Hello, 大家好，我是 Edmund, and welcome back to Edmund's Maths. Now, today we're going to be looking at the limiting cases of the equations which we derived a few videos ago. So, join me and let's get on with it. Now, we are looking, of course, we know that we have fully solved the problem of two masses in deep outer space coming together. Now I'm going to be taking a certain limiting case and hoping that in this limiting case, our exact solution looks like how we expect it to look. So the limiting case I'm going to be looking at is if our mass m2 is the Earth. So mass m2 will be the mass of the Earth. m1 will just be an ordinary object. So, for example, it could be a bottle, it could be a rock, a stone, or even a pen. We are essentially going to be focusing in on the case of an object falling towards the Earth's surface. So something like this. Okay. Now, this is, of course, this diagram is not very much to scale. I mean, of course, the object will not be the same size as the Earth. I'm talking about an object much smaller than the Earth, and of course, the object will be much closer to the Earth. I mean, what I mean by this diagram is that the Earth, this position the Earth is at, this is actually the centre of mass of the Earth. So the centre of mass of the Earth will be here at the position A on our x-axis. And the object will actually be at the Earth's surface. So, in fact, a more diagrammatically correct diagram would be something like this, where this line is the Earth's surface. So this distance would be the radius of the Earth. Okay, setting it up on the coordinate axes that we made before, this point here, well, remember on our x-axis, we said that this point here was x equals 0, and this point here was x equals a. So, given that we are talking about an object just falling towards the ground, this object isn't really going to move very much. It will start some distance above the Earth's surface, then it will fall, and at the Earth's surface, it will stop. So this object will start and stop, on this diagram. This is like the radius of the Earth, which is, thousands of kilometers. And the object will only be falling, 10 meters, in the order of 10 meters, maybe 100 meters, 1 meter. So, the objects won't actually be moving, in terms of this the scale of this diagram, the objects will only be moving a tiny, tiny bit. So we can actually model this distance a between the centre of masses of the object. We can model that just as the radius of the Earth. So we can actually take a to be equal to the radius of the Earth, because if the object is placed at distance 0 away from the Earth's centre, then the centre of the mass of the Earth will be a distance roughly re away. Okay. So another parameter in our problem is that a is going to be equal to the radius of the Earth. Okay, and of course m1, the mass of the object, well, the mass of the object m1 will be, some ordinary size. It will be something like, 10 kilos, 1 kilo, 100 kilos. It won't be anything like the size of the planet. So m1 will sort of be roughly of order 10 kilograms, something along that. Okay, we can now sort of look at what the numerical values of these will be. So the mass of the Earth, that's, approximately 6 times 10 to the 24 kilograms. The radius of the Earth is approximately, well, it's about 6.4 times 10 to the 6 meters. So we could take that as about 6 times 10 to the 6 meters. And now we are ready to start looking at the actual solutions. But first we actually need to look at kappa. But we'll calculate that in a minute. So we know that the object's trajectory will have a trajectory that looks like x1 of t is equal to, now before we had a times m2, a times m2, a is re, so it will be re, radius of the Earth, times by m2, which is mass of the Earth, divided by m1. Let's just call the mass of the object m1. Let's just keep it as m1 for now, plus the m2, and m2 is the mass of the Earth. Okay, and this will be multiplied by the inverse incomplete beta function half 3/2 of kappa times t. Okay, and the second mass, i.e. the Earth, of course, when something, what the solution of our problem actually says is that, of course, when something falls towards the Earth will also fall towards it. So the Earth will have a trajectory of its own, and of course we've solved for that trajectory before. We know that x2 of t will be given by a, which is given by re in this case, 1 minus mass of, well, it'll be m1 on the top, isn't it? Then m1 plus mass of the Earth, times by inverse incomplete beta function half 3/2 of kappa times time. Now, for x1 of t, we can see that the mass of the Earth is on the top and bottom of the fraction, and the mass of the Earth is much, much greater than m1. So this fraction, me over m1 plus me, will be roughly 1. However, in this case, we have m1 on the top, and this means that because we have me on the bottom, this fraction will be something of order, 10 to the minus 23, because we have, 10 on the top, 10 to the 24 on the bottom, and we have 1 here, and this is much, much, much less than 1. So actually, this part of the trajectory of x2 will pretty much be 0. That'll be approximately 0. So actually, to a good approximation, x2 of t will just sit at its own coordinate. It won't change with time. So that actually makes sense, because of course when something falls towards the Earth, the motion of the object falling is much, much more than the motion of the Earth. Great, so that's good. That means we actually don't need to think about the Earth's motion whatsoever. We can be confident that it will pretty much stay where it is. Right, so sorry about that. So all we have to think about now, we know what the sizes of RE, ME, M1 and ME are. We just have to think about the size of kappa now. So kappa, we know, is given by this equation up here, which you've seen enough times by now not to need to explain it again. So we can actually plug the numbers in, and these are only approximate numbers, so I'm just going to use the approximation symbol. My physicist hat is on now. It will be equal to approximately 2 times, now G is given by 6.67 times 10 to the minus 11 newtons, kilograms to the minus 2 meters squared, but that's going to be roughly 7 times 10 to the minus 11. M1 plus M2, now M1 is just 10 and ME is like 10 with another 23 zeros on it, so we pretty much only have to consider that the mass of the Earth here, because M1 is negligible, so this will be 6 times 10 to the 24, to a very good approximation, and we divide it by a cubed. Now a is the radius of the Earth, which is 6 times 10 to the 6, and we cube that, and then we take the whole thing to the power of half. Now if you work this through, we have 2 times 7, which is 14. The 6 cancels with one of the 6's on the bottom, so we end up with 2 times 14 divided by 36 squared, which is 14 divided by 36. 14 divided by 36 is, quite roughly 18 divided by 36, which is a half. So we can say that this is roughly a half times. Now the 10 to the minus 11 will cancel 11 from the 24 here, the 10 to the 24, and we get 10 to the power of 13, and we divide that by 10 to the 18, which gives us 10 to the minus 5. But remember, all of this is being taken to the power of a half. So we get 1 over root 2 times 10 to the power of minus 2.5, which is 10 to the minus 2 times 10 to the minus a half, which is 10 to the minus 2 times 1 over root 10. And we can actually combine, we can actually see now that this is 10 to the minus 2 divided by something like the root 20, which is, root 20 is like roughly 4 or 5. So this will be like, kappa will be roughly like 0.2 times 10 to the minus 2, seconds to the minus 1. And so, because this is roughly of order 10 to the minus 1, we can say with confidence that the order of magnitude of kappa, because we're doing a limiting physics problem here, so we only really care about orders of magnitude anyway, kappa will be of order of magnitude 10 to the minus 3 seconds to the minus 1. Okay, I'm just going to leave that up here for now. Now, this here is quite significant. Now, whenever a physicist sees a small quantity, they get very excited because it usually means that they can expand something in something small. Gives us a little hint of what might happen later. But what can we actually see the significance of this now? Well, kappa is seen inside the inverse incomplete beta function, and it's multiplied by t. So let's see roughly what sort of kappa t will be. So if we have kappa t, now kappa is already like of order 10 to the minus 3. So in order for this thing to remain small, then we need to have so for kappa t still being much less than 1, then t can be anything of order roughly up to 10 to the 2, because then kappa t will be something like 10 to the minus 1, like 0.1, which indeed is much less than 1. So as long as this object falls for less than 100 seconds, or just 10 seconds, 1 to 10 seconds, which will comfortably be under that limit, then we have this being true. Okay, so what significance will that be? So what have we concluded so far? Well, we've got this trajectory here. We know the Earth doesn't move, and we know that as long as this thing doesn't fall for more than 10 seconds, then we can comfortably assume that this is true. Now, what sort of motion can we have when t is less than 10 seconds? Well, of course, when I drop this, the time is only about 1 second, less than 1 second. If something falls from a roof, it takes about 5 seconds to hit the ground. If something falls off a cliff, it takes about 10 seconds to hit the ground, roughly. So actually, this motion is covered by, something falling off a cliff, something falling off a roof, something falling off any kind of everyday falling under gravity. So this limit actually describes anything that's falling near the Earth's surface and is only falling, like the size of a cliff or the size of a house. So this limit is true for anything falling near Earth's surface, which is sort of the limit in case we want to look at and see that it looks the way we want it to. Now, of course, things like skydivers, you could argue that they're falling near the Earth's surface. However, our model wouldn't really work for them, because when you get to distances that are very large and falling times that are, hundreds of seconds, then you'd have to take into account air resistance. And that is something we haven't taken into account whatsoever yet. In fact, with the model, with the whole equations of motion and derivation we've done in the last 4 videos, it would actually be impossible to analytically solve this if you took air resistance into account. So we're not thinking about air resistance. We're sort of just thinking about everyday sort of falling when you can neglect air resistance. Okay, great. So now what can we do next? A physicist loves it when you can have some sort of limit like this, because it means you can make some sort of expansion. And indeed, with this inverse incomplete beta function, you can now expand this in powers of kappa t. And the expansion we're going to be using is an expansion that I will derive in the next video. So you're just going to have to trust me right now that this is true. Okay, so for small kappa t, i.e. for kappa t much less than 1, then beta half 3/2 kappa t is I suppose you could say it's asymptotic to kappa squared t squared. In fact, what I'll do is actually say this for a general argument. So for general inverse incomplete beta function x, it's asymptotic towards x squared over 4 as x tends to 0. Or in other words, inverse incomplete beta function half 3/2 of x is equal to x squared over 4 plus some sort of higher order terms. So these higher order terms will be negligible compared to this in the limit of x being much less than 1. Great, and that suits what we need. So what we're going to do now is expand this inverse incomplete beta function in powers of x up to order x squared and see what we get. Okay, so let's shove in our expansion. Now we have x1 of t is equal to radius of Earth times mass of Earth divided by m1 plus me multiplied by this. Now remember, this will be the argument squared divided by 4 in the expansion. So we will multiply this by kappa squared t squared over 4 plus some higher order terms which will be of order kappa cubed t cubed, and these will be negligible. Okay, so we can now sort of expand out the bracket, and actually when you expand out the bracket will actually look the same, because when you multiply this, which is something, some constant, which doesn't depend on kappa or time, when you multiply this by this thing, then this term will still be of order kappa cubed t cubed. So we can actually just expand this out and say that we're only multiplying this term by kappa squared t squared divided by 4. Okay, let's see what kappa actually is. So kappa is given by this. So kappa squared is just the thing inside the brackets without this square root. So we can shove that in. So we get radius of Earth, mass of Earth, divided by m1 plus me times by kappa squared. Now kappa squared will be given by 2 times g times m1 plus me, because remember m2 is mass of the Earth, divided by a cubed, and a is radius of the Earth. So we have radius of the Earth cubed, and there's no square root because we're squaring it, and you multiply it by t squared by 4, plus some higher order terms that we don't care about. Okay, got some beautiful cancellations here. So let's cancel off. We get the m1 plus me, that cancels nicely. This radius of Earth cancels with this cubed and makes it into a squared. And this 4 cancels with this 2. Sorry, the 2 cancels with the 4 and turns it into a 2. Okay, so I'm going to take this 2 out to the front, and then I'll continue my working. So we get x1 of time is equal to a half multiplied by, now what have we got left? We've got big G, mass of the Earth, divided by radius of the Earth squared. So we've got big G, mass of Earth, times radius of Earth squared, times by t squared, plus order terms which are higher and we don't care about. So we've got this solution. Now, okay, we've got x1 of t is equal to half times this thing times t squared. Smelling something here. Well, if we numerically compute this, we actually get that this thing is roughly of order of 10, and the units will be meters per second squared. What does that remind you of? Well, indeed, when you look at Newton's equations, when you look at Newton's law of universal gravitation and the gravitational field, this thing is actually the gravitational field strength at the Earth's surface. So you should be familiar with this. This is actually G. Okay, so let's just go ahead and replace this. So we have x1 of t is equal to half g t squared plus some higher order terms that we don't care about. And is that what we expect? Well, when something moves close to the Earth's surface, they can be modelled by the constant acceleration equations. Now, the constant acceleration equation for displacement is that, and hopefully you all know this, s is equal to ut plus half at squared. And in this problem, the initial velocity of this is 0, because that's what we defined in our initial conditions when we solved it. And a is equal to g, because when something's moving towards the Earth, the g is also known as the acceleration due to gravity. And indeed, we recover s is equal to half gt squared. So, in our limiting case for our analytic solutions, we actually recover the suvat equation for that, which is absolutely fantastic, because this shows that our exact solution is valid in a very important limiting case. Okay, so that makes me very happy, because what we've done really is done a sanity check of our solution and showed that it does the appropriate limit, which is what we want. So just bear with me a sec, I'm just going to wipe the board clean. Now, we also haven't thought about the position of the position function definitely behaves as we expect it to behave in the limiting case of something moving near the Earth's surface. But what about the velocity? Well, let's have a look at the velocity. Now, the velocity function, if we remember, so we're now looking at x1 dot of t. If you recall, that's equal to, what was it, a times m2. Now, a is the radius of the Earth, m2 is mass of the Earth, divided by m1 plus m2. And now we multiply this by kappa because actually there was some differentiation going on in finding this, so we had a factor of kappa in there. And then we times it by, now I'm going to need the extra space here, inverse incomplete beta function, a half 3 over 2 of kappa times t, divided by 1 minus inverse incomplete beta function half 3 over 2 of kappa times t. Okay, now we want to expand this for small kappa t, so when kappa t is much, much less than 1, which is the thing we're doing, then we can expand this. So we get radius of Earth, mass of Earth, m1 plus m Earth times by kappa times by, now this top one will give me kappa squared t squared over 4 plus order of kappa squared kappa cubed t cubed divided by 1 minus kappa squared t squared, which will be of order of kappa squared t squared. Okay, now what I'm going to do is I'm going to take this outside the bracket, and of course we're taking this to the power of a half. I'm going to take this outside the bracket, so if I take this and shove it outside, then we have to take it to the power of a half, so we get kappa times t over 2, because we're just taking the square root of what was inside the bracket. Open bracket again, and this is now just going to be a 1 left behind, and we've actually taken away a something of order kappa squared t squared, so we now need to make that kappa t. Okay, and it's all taken to the power of a half. Now, we can do a binomial expansion of this, and 1 plus something of order kappa t to the power of a half, so we have x1 dot of t is equal to all this gubbins times by all that gubbins times by 1 plus order something to the power of a half. Now, if we binomially expand that, that gives us 1 plus order something of the same thing, because you just times it by a half, and then that's still of order kappa t, and then it'll be something to the power of minus a half. Now this will be 1 plus, because it's a binomial expansion, something of order kappa squared t squared again, because essentially you can say that this is to the power of minus a half, and then you can do a binomial expansion, and it still gives you something the same that looks like this. Now if you expand this out, this gives you 1 plus something of order kappa squared t squared plus something of order of kappa t plus something of order of kappa t cubed. So what do we only care about the leading term, so really this is just 1 plus something of order of kappa t on its own. Okay, so all this stuff is just boils down to this. When you multiply everything out and you think about what the largest terms are, this is what this is. And we can put the gubbins back in again. So x1 dot of t is equal to re times me over m1 plus me times by, now this kappa is multiplied by kappa, so you get kappa squared, and kappa squared is equal to 2 times g times m1 plus me divided by a cubed, which is the radius of the Earth cubed, and we have a half there from that factor, times by t, times by 1 plus something of order of kappa t, and we know that this is going to be small and negligible, so we don't care about it. Once again, the m1 plus me cancels, the 2's cancel, and again the radius of the Earth cancels with the 3 to give radius of the Earth squared. Okay, so what we're left with is x1 dot of t is equal to big G times mass of the Earth divided by radius of the Earth squared times by t, and plus something of order kappa times t, which will actually be kappa t squared, but pretty much this term is small compared to the other one, so we don't care. In fact, this will indeed be something of order kappa squared t squared, because we already had kappa t in there. Brilliant. So, what is this? Well, remember, this is acceleration due to gravity close to the Earth. So indeed, this gives us g times t plus higher order terms, which we don't care about. Now, what does this smell like? Remember this, the constant acceleration equation for velocity is v is equal to u plus at. In this case, u is 0, and in this case, a is g. So the equation we expect is v is equal to gt. And indeed, this matches with our exact solution in the limit that we're talking about, something moving near the surface of the Earth. So, that concludes our two masses moving in space problem. We've derived the equations of motion, we've solved the equations of motion, and we've looked at the graphs of the solutions to show that they make sense, and we've also looked at the limiting case and showed that that makes sense and agrees with our previous theory, a simpler theory which is assuming that acceleration is constant. I just want to say, for those of you who've been watching this playlist, I really appreciate your support. I know some of you have been liking my videos, so thank you very much for that. And continue joining me for Edmonds Maths. We're going to be doing differential equations, some random videos that people have requested, and there's much more to come. So stay tuned, and thank you for watching.